Hello everyone, welcome to lecture 2 of week 3 of the course Simulation of Modern Power Systems, in which we continue our discussion on the module Power Flow Analysis. And in this discussion, we will take a look at a very well known, popular, prominent power flow technique used in industry grade softwares for solving power flow for large power networks. And that technique is well known as fast decoupled method, fast decoupled power flow, FDPF, and so on. The last lecture we discussed about a very specific form of power flow in which rather than a slack bus or one single slack bus accounting for all generation load mismatch, to be precise, real power generation load mismatch and real power losses, there can be an economic way of ensuring that multiple generator buses can share this real power generation load mismatch and real power losses, so that the overall system operation from real power generation, which satisfies the corresponding real power demands, can be minimized, which is where the basics of economic dispatch was discussed a bit in the beginning of the last discussion, and it ended with the application of economics to power flow, which we call as participation factored power flow. The discussion of participation factored power flow was for voltage phasors when they were represented in rectangular coordinates. There was also an example which sort of clarified as to how this participation factored power flow works when voltages are measured in rectangular form. The same discussion is also applicable for voltage phasors when they are to be represented in polar coordinates. The discussion that we will have today will require a recapitulation of the Newton-Raphson method when the voltages, all bus voltage phasors, they were represented in polar coordinates, and that is where the well-known fast decoupled power flow or decoupled power flow comes in. So, I would request all my viewers, learners to please look at the corresponding discussion where we discussed Newton-Raphson power flow for voltages in polar coordinates and length, and then follow this discussion. So, we have all seen or learnt that Newton-Raphson power flow, NRPF, in full form it is Newton-Raphson power flow, irrespective of whether it is polar version or rectangular version of voltage. In the kth iteration of Newton-Raphson technique for solving power flow, we get a equation, update equation, where J is the Jacobian matrix, f of x at latest solution xk is the mismatch vector, and delta sk is essentially the difference between the next iteration update and the current iteration update. In details, if one has to understand what these vectors and matrices are, then for voltages, bus voltage phasors in polar coordinates, delta x is change in voltage phase angles and voltage magnitudes, respectively for buses numbered from 2 to n, and voltage magnitudes being for PQ buses. Inherently, I am making the assumption here that for the given power network, bus 1 is the angle reference bus for which theta 1 is 0 radians or degrees, and V1, the magnitude, is specified as the specified value from active power loss minimization for the corresponding largest generator connected to bus 1. Consequently, we can also write the mismatch vector f of x in terms of changes in real power injections and reactive power injections, respectively for buses numbered from 2 to n and for all current PQ buses. If this definition is true and these vectors are mathematically consistent, then we will have this Jacobian matrix, which would be a square matrix having 4 distinct submatrices, the elements of which have been explained at length or discussed at length in the Newton-Raphson version of polar coordinate voltage phasors. So if we now expand or put in the corresponding representations into this compact equation and try to see how these updates appear in x in terms of changes of real power injection or reactive power injection, then we will have a form as shown over here, wherein what we see is that essentially these Jacobian matrix or these submatrices Jp theta, Jpv, Jq theta and Jqv, they are essentially sensitivity matrices which indicate that if delta P and delta Q change by some unit value, what would be the corresponding change in the associated bus voltage phase angles and the corresponding voltage magnitudes. Now, coming to the history or origin of fast decoupled power flow, I would request all my learners, viewers to please refer this or go through this classical paper which was authored by Brian Stott and Onguk Alsac. Alsac being a PhD student of Professor Stott. They later on, so this paper came in 1974, but it took almost 1 decade or more than 1 decade for the power engineering community to understand the importance of what these two great electrical engineers have done. So essentially FDPF, if its origin were to be traced, it was well thought of, well planned for power networks, specifically for power flow in 1974. But somewhere in 1984 and 85, the rest of the engineers, researchers, they started observing this great technique. So this technique that Alsac and Stott together thought derives its motivation from Newton-Raphson power flow. The main challenge or problem that they tried to sort of get rid of or try to solve was that in every iteration of Newton-Raphson power flow, this Jacobian matrix, which would be a large square matrix, often a sparse matrix, but a large matrix, for a large power network, it would require continuous evaluation of this Jacobian, and also it would require its own factorization so that the corresponding state variable changes can be known, provided these mismatches are also being evaluated. So every iteration of Newton-Raphson involving this calculation and factorization of this huge Jacobian matrix was a big challenge, because 50-60 years ago computational capability was very limited, and hence even though at the outset Newton-Raphson technique on paper was very good, but there were not commercial solvers or commercial platforms available in which Newton-Raphson could be tested for the then operating power networks. And that's where Alsac and Stott, they figured out, or through their experiences, they did lot of experiments, trials, all simulation based trials, and came up with this fast decoupled power flow method. At the outset, I would again repeat that fast decoupled power flow, unlike Newton-Raphson and Gauss-Seidel, is a technique which is specific only for power flow analysis. It cannot be or need not be used for solving generic mathematical equations of the form f of x. F of x in this case is specifically power flow equation. So the principles that they tried, tested and sort of proved in this paper, classical paper, was that they observed that for a network, power network, which is mostly a reactive network in the sense the inductive component of transmission lines is much larger compared to the corresponding resistances. In such a network, the change in voltage phase angle is primarily gets affected or affects the change in real power flow of lines, and the corresponding change in reactive power flow is not that significant. Essentially, they try to sort of bring in the fact that real power, the corresponding injection or the flows, they are strongly coupled to the voltage phase angles. Whereas any change in voltage magnitude, it has a very prominent strong effect in reactive power flows and corresponding injections. The corresponding change in real power flow or injection is not that high, essentially meaning that Q is strongly coupled to voltage. So, in terms of combinations of coupling, if I were to say, Alsac and Stott prove that P and theta, they are strongly coupled. Q and V voltage magnitude, they are strongly coupled. Then comes the coupling of Q and theta, and then comes the coupling of P and V. They were just trying to prove that these couplings, they are much more stronger compared to the couplings which are present in the last two combinations. They did not say that Q is independent of phase angle or real power is independent of voltage. In fact, strong correlation of P versus voltage magnitude is a reason why voltage stability or voltage instability is a primary subject or topic of concern or discussion, which we will also discuss towards the end of this course. So, as I mentioned, Jacobian is essentially a sensitivity matrix, and by first principles, Jp theta is having dominant in the sense comparatively in terms of magnitude, Jp theta elements are stronger or larger than Jq theta elements, and similarly Jqv elements are dominant, numerically dominant compared to Jpv elements. And that is also true because that's the reason why Jacobian, as I mentioned in the last slide, is a sparse matrix. So that's and the sparsity essentially comes because of lots of zeros present in Jq theta and Jpv elements. The number of zeros which are present in Jp theta and Jqv elements, they are very small, very small. And thus, we can rewrite the Newton-Raphson power flow equation, update equation in approximated form as mentioned over here. Please note that the discussion that I am having or the idea that Alsac and Stott placed, it derives its motivation from Newton-Raphson version of polar coordinates. The same discussion or same exercise has been tried, but it hasn't reached its maturity. That is, can fast decoupled power flow be also derived and devised for Newton-Raphson method when voltage phasors are in rectangular coordinates? That's still an area of research. People are still, some preliminary work has been done, but it hasn't reached its maturity yet, as the way the fast decoupled power flow in the current form works so well when voltages are in their polar coordinate version. So, based on these approximations, we can have these two equations. So, using the strong P theta and QV coupling, we have been able to get these two equations again in an approximated way. So, now the power flow equations, they are decoupled in the sense, if I have to find change in voltages, then I will only focus on the change in reactive power injections. I will not be bothered with change in real power injections. Similarly, if I have to find changes in phase angles, I will only be concerned with changes in real power injections. I will not be concerned with what are the changes in the reactive power injections. And that is where the decoupling aspect comes in. The equations are decoupled, but they are still not independent equations. The reason for why they are still not independent is Jp theta and Jqv submatrix elements, they are still functions of both voltage magnitude and phase angle. Please recheck the element expressions for these submatrices in the corresponding discussion of Newton-Raphson power flow for voltage polar coordinates. There you would very well see that Jp theta and Jqv both are still functions of voltage magnitude and phase angle, and that is the reason why they are still not independent. ALSAC and STOT went one more step ahead, and then they realized that, okay, this independency, can it be achieved? Again, they tried lot of simulation based experiments, and that is where I would like to mention that fast decoupled power flow, unlike Gauss-Seidel or Newton-Raphson technique, doesn't have a mathematical basis associated to it. It is a fully, completely experience-based method which ALSAC and STOT came up with. To bring in furthermore independency between the two decoupled equations that we have present here, ALSAC and STOT observed that for transmission networks which are well designed and are operating at moderately low levels, that means the load levels are not very high, the voltage phase angle differences are very, very small in terms of radians, and hence sign of phase angle difference can be approximated by the phase angle difference itself, whereas the cosine terms, they can be approximated as 1. Since the transmission network is highly inductive, so line susceptances are much, much larger than the corresponding line conductances. Essentially, it comes from the fact that R by X ratio of transmission systems is very, very low. It's a very, very low value because R is very low, but the X values are very high. So, overall R by X ratio is very low for transmission networks. The reverse case happens for low voltage distribution networks, which results in the fact that Bij terms are much, much larger than the Gij terms, and hence we can have Bij cosine factor dominating the corresponding term present on the left hand side. Also, the reactive power injection at a bus during normal operation is much, much smaller than the reactive power which is injected due to self-susceptance. So, they also established this inequality fact. And using these approximations, they tried to see that can Jp theta and Jqv be made independent, in the sense, can they be made independent of dependency in terms of both voltage magnitude and phase angle. So, if we bring in those approximations that we have seen, sine of theta ji is, so basically cosine of this phase angle is can be approximated as 1. Gij sin theta ij based on this fact is much, much smaller than the term present in this encircled part. So, this can be made 0, and hence the off diagonal term of Jp theta can be written simply like this. Similarly, we can have diagonal term of Jp theta, since Qi is very, very small. So, it can be simply approximated as minus Vi square Bii. Likewise, for off diagonal term of Jqv matrix, we can have this approximation, and likewise for the diagonal term of the Jqv matrix, which is of the similar form as shown over here. So, what we see here is that Jp theta and Jqv are now independent of the voltage phase angles, because the phase angle differences are very, very small, but they are still dependent on both voltage magnitudes. So, that is where the next trick came in. So, for time being, if we use these elements and put them in the decoupled first half equation that we saw, which is where we call it as half iteration equation. Unlike Newton-Raphson technique, where iterations are always going to be integers, ALSAC and STOT stated that they would count p theta solution to be one half iteration and QV equation solving to be the another half iteration. When in one iteration both this equation as well as the next decoupled equation are solved, only then one iteration of fast decoupled power flow is counted, and that is where the notion of half iteration comes in. So, if we focus on the first decoupled equation and put in these off diagonal and diagonal values in the Jacobian matrix, then we see that we have voltage terms present along the B elements, and the rest of the product term, of the voltage is being present as a denominator in the real power mismatch equation. Assuming, and thus came the last mile resort, that typically voltage profiles are in transmission network are close to 1 per unit when the system load is not very, very high. So, if we can put all these voltage magnitudes to be 1, irrespective of whether these are PV bus, PQ bus or slack bus, then essentially on the left hand side we would have this matrix which is only function of the imaginary component of Y bus, which is where we define B dash matrix. Assuming voltage magnitude to be not very different from 1 per unit, this matrix simply boils down to B dash. Again, here the assumption is bus 1 is the slack bus, which is where you would see indexes running from 2 to capital N being the number of buses in the power network. Similarly, for JQV half iteration, if we write this blown up matrix and substitute the corresponding off diagonal and diagonal terms, and using the fact that voltage magnitude is not very different from 1 pu, we would have the second half equation, which would again be a function of the imaginary component of the Y bus. And since QV half iteration or QV equations pertain only for PQ buses, here we would have only the PQ buses, because voltage magnitudes updates would only be obtained for PQ buses. For PV buses, voltage magnitudes updates are fixed. Similar to the fact that for bus 1 being slack bus, its angle reference is typically fixed or chosen to be 0 radian. And now the equations that we have, which are E1 and E2, they are decoupled as well as they are independent. Independent in the sense, what you would see is that on the left hand side, B dash matrix and B double dash matrix, they are functions of imaginary component of the Y bus admittance matrix, and hence continuous evaluation is not required. Continuous factorization is also not required. We factorize B dash or inverse B dash and B double dash once, and the only thing that we need to do is obtain this mismatches delta P and delta Q. The Jacobian inverse remains constant, and that is where the uniqueness of fast decoupled power flow comes in. So B dash and B double dash, they are constant matrices. They depend only on the network parameters. These are evaluated once, and the associated inverse factors are stored for all fast decoupled power flow iterations. To make things furthermore faster, which is where the last fifth point of ALSAC and STOT comes in, is that the number of iterations involved in fast decoupled power flow are relatively higher, although the number of iterations are higher in fast decoupled power flow compared to Newton-Raphson power flow for polar coordinates. But since the constant matrice part is involved, the effort or time required in fast decoupled power flow is tremendously improved, and which is where quick power flow solutions can be obtained. And that's the reason why it is very useful in contingency analysis, offline power flow analysis. Since there are approximations involved in fast decoupled power flow, its convergence is not that good compared to Newton-Raphson power flow, specifically for points where the load reaches the voltage unstable condition. In fact, Newton-Raphson power flow goes a mile ahead compared to fast decoupled power flow. Fast decoupled power flow has poor convergence even way before the voltage instability condition. So to make FDPF furthermore efficient, which is where the last fifth part of ALSAC and STOT contribution came in, that since we are worried about P theta half iteration, where we were focused on obtaining voltage phase angle for known real power injections, why should we consider all elements in Y bus, specifically while we are evaluating B dash, which have not much to do with the phase angle dependency or change? So ALSAC and STOT suggested that we evaluate bus admittance matrix for the given power network, but for P theta half iteration, we will neglect the presence of line resistance, we will neglect the presence of shunt susceptances, both half line charging as well as capacitive susceptances, and voltage regulation taps, because these devices, they mostly pertain or affect the voltage magnitude. They have less effect or change in the corresponding voltage phase angle. So we evaluate the bus admittance matrix. We call that to be Y bus dash, which is evaluation of bus admittance matrix the way it has been discussed, but ignoring the presence of line series resistance, shunt susceptance, and voltage regulators. Once we evaluate corresponding Y bus dash, assuming bus 1 is slack bus, we extract the elements of 2 to n, 2 to n, which is what gives us the B dash matrix. So if we ignore the network elements, essentially Y bus is being evaluated only when we have line series reactance and phase shifting taps, because phase shifting affects the voltage phase angle directly. Same is the case with line reactance. So this is our B dash matrix. Similarly for B double dash, we evaluate the Y bus the way it has been discussed, but we ignore only the presence of phase shifters. We consider the presence of line series resistance, shunt susceptance, voltage regulators, as well as line reactance. So essentially, once we evaluate that Y bus and call it as Y bus double dash, we extract the corresponding PQ elements, PQ buses elements from the Y bus, because voltage magnitudes are only to be obtained for PQ buses only, whereas phase angles in the first iteration are to be obtained for all buses from 2 to n. Bus 1 angle is not necessary. So Y bus double dash and Y bus dash, they are two different Y buses. Their evaluations are on similar procedure, similar lines, but for a given power network, given that the lines would have resistances, reactances, considering the presence of the respective elements as discussed here and discussed here, the corresponding B dash and B double dash matrices are going to be different. The reason why this is to be done, the details of it are explained well in the fast decoupled power flow paper by Alsack and Stott, the reference to which I have given in the 4th slide. Please refer to that. There is no mathematical proof as to why this works, as I mentioned. It just works, and that is how Alsack and Stott came up with this method. So to summarize the technique as to how it works, we evaluate B dash and B double dash from corresponding Y bus dash and Y bus double dash matrices. We start with an initial flat start of voltage. We evaluate the corresponding real power mismatch and reactive power mismatch equation. The way it is to be evaluated, when we evaluate these mismatches, there is no approximation involved here. It's the perfect way of evaluating mismatches using Y bus matrix, the actual Y bus matrix, and not Y bus dash or Y bus double dash. And when we do this step, since the first half iteration is for P theta half iteration, we are not bothered whether PV PQ or PQ PV switching is involved. This would come into picture when we try solving for the QV half iteration. Since we are talking about the first half iteration which pertains to P theta, before we start solving the P theta half iteration, we check whether delta P and delta Q, these mismatch vectors, are they meeting the tolerance or not. By tolerance, I mean if I denote delta P by a voltage vector, delta Q by a voltage vector as my mismatch vector, whether the infinity norm of this vector is less than tolerance, which is typically 10 to the power minus 4 or 10 to the power minus 5, depending on the way we choose. If the tolerance is met, then there is no need to solve the solution. Whatever solution we have at hand, that is the final power flow solution. If it is not met, then we solve E1, which is the first half of P theta, the fast decoupled iteration, and update the voltage phase angles. By update, I mean if I am talking about the first iteration, then theta 1 would be theta 0 plus delta theta, which is where the Newton-Raphson update also comes into picture. So we update the Newton-Raphson voltage phase angles the way they were done in Newton-Raphson power flow. Once the P theta half iteration is done, then we again re-evaluate delta P and delta Q for the QV half iteration at the known voltage phase angles, latest voltage phase angles and voltage magnitudes. Now, since we are focusing on QV half iteration, so the PV PQ switching check has to be required. The process remains the same as it was done for Newton-Raphson power flow and Gauss-Seidel method. Before solving QV half iteration, we check whether the convergence has been met or not. If it is true, fine, the solution has been obtained. If not, then we find B double dash based on the number of PV PQ buses that are involved. For every PV to PQ bus conversion, the size of B double dash would increase by 1. For every PQ to PV conversion, B double dash size would go down by 1. And depending on that, we solve for equation E2, find the voltage updates, and then update the voltages just by adding them to the previous value, the way it was done for Newton-Raphson power flow. And then this process repeats from step 3 being the part which is the step present over here. This continues and goes on till the iterations mismatch vectors are less than the tolerance. Since there are two checks for mismatch vectors, often in fast decoupled power flow, iteration happens in odd, I would say, partial integers like 10.5, 11.5, 1.5, 2.5. That is a possibility, and it does happen in practice. So as I mentioned, Q limit part I have already stated. For every PV to PQ switching, dimension of B dash increases by 1. For every PQ to PV switching, dimension of B double dash goes down by 1, and hence this challenge or this issue still remains an open-ended problem for fast decoupled power flow. That if B dash dimension is changing, so corresponding factors would also change. Although the elements may not change, but the factors are definitely going to change. So it's still a challenge. I'll conclude the discussion with an example of fast decoupled power flow. The system data is the same data that we discussed in the last two discussions, one being on Newton-Raphson power flow for rectangular coordinates and the other being on the participation factored power flow. It's the same system, same data, where bus 1 is slack bus, bus 3 is PV bus, bus 2 is a PQ bus. For this network or given network, since there are no transformer taps, there are no phase shifters, there are no voltage regulators. So in this case, the Y double dash matrix that we would evaluate for fast decoupled power flow, it would be same as the actual Y bus, which is essentially what has been shown over here. This is the actual Y bus. The next paragraph is just a summary of the data that is given for the given network. Since we also have to find Y bus dash while ignoring line resistances, shunt acceptances, so essentially when we find Y bus dash, we ignore this to be 0 while retain J.1 as it is. We ignore this presence as well as this substance. So if you ignore these elements, then the network lines that we have, they pertain to the example that we have had in Newton-Raphson power flow when voltages were in polar coordinates. And that's the reason why Y bus dash matches exactly with the Y bus that we saw in the polar version of Newton-Raphson power flow. The unknowns are voltage phase angles of bus 2 and bus 3 and the PQ bus voltage. The known voltages, the variables are known. At this flat start, we evaluate the injections, the values of which have already been given. The expressions for these injections, they have already been given in the Newton-Raphson version for rectangular coordinate. Then we find the mismatch vectors. We find delta P vector as well as delta Q vector. The corresponding values are given. Please spend some time in cross-checking whether these values are correct or not. I strongly believe that these are correct. And then we see that the overall mismatch vector, its highest element, the infinity norm, which is pertaining to this element, is definitely not less than the tolerance that we have chosen. So hence, FDPF P theta half iteration continues. For P theta half iteration, we find B dash, that is its elements from Y bus dash, which is this 2 cross 2 matrix. We already know the mismatch vector. Put in the corresponding values, we get this as our latest voltage phase angles. We update the X vector and call it to be 0.5 as the iteration number. All voltage phase angles are updated. The voltage magnitude, however, still needs to be updated. So at this solution, we again evaluate the mismatches, the corresponding injections using the actual Y bus. And we see here that bus 3, which is a PV bus, the check has to be made. Its generation is 0.3666. There is no load connected, which is still within its given limits of Q min and Q max, and hence bus 3 remains as a PV bus. We find the other injections and call those corresponding superscripts as 0.5 iteration. And since bus 3 remains as a PV bus, it's now time to find again the mismatch vectors. The values have significantly changed. And here if we see delta M has the largest value of 2.3127 as an element, which indicates that its tolerance is never met. So we solve for the QV half iteration since we have only one PQ bus, which is bus number 2 at this given iteration. So we get B double dash, put in those corresponding numbers and values, and we get V2 as 0.7951. With this, the one full iteration of fast decoupled power flow is complete. The overall solution converges in 10 iterations with bus 3 switching to PQ status after 1.5 iterations. That means 1.5 iteration means 2 P theta half iterations and 1 QV half iteration, and it never comes back to the PV status, with final solution being exactly the same that we obtained in Newton-Raphson method for rectangular coordinates. If we lower down the tolerance furthermore, that is make it 10 to the power minus 5, the convergence happens in 12.5 iterations. All these numbers, all these vectors, values, they have been obtained from a code written in MATLAB, which is what I was explaining the other day, other discussion, that MATLAB is a very well-known tool used by power engineers for solving such exercises. The next discussion will be on a very specific topic which derives its motivation from past decoupled power flow. We will call that as DC power flow. There is a reason why it is called as DC, and it does have its importance or usage for giving a quick picture of what would be the voltage phase angles provided certain conditions are met. DC power flow doesn't provide voltage magnitudes, but it is very good in providing a good picture of what the voltage phase angles would be and what would be the real power flows on the lines, which helps the operator assess that rather than going into very accurate power flow techniques which would take comparatively lot of time to get the solution, can we have a one-step linear approach, which is the DC power flow, from which we get the voltage phase angles in no iterations, just one iteration we get the voltage phase angles, and that would be saving a lot of time, although the accuracy would be low, but the quick assessment of a given network disturbance can easily be perceived, analyzed or observed through this technique, and that is where the importance of DC power flow comes in. With that, I conclude this discussion. Look forward to more discussions on DC power for the next discussion. Thank you.